Welcome back to the course Basics of Mechanical Engineering Theory. I am discussing the tutorial on the power cycles. I have discussed in the third tutorial of this course the auto power cycle in the previous part. This is the second part of the third tutorial where I will discuss the diesel power cycle. To recall the concept of the diesel power cycle is just like auto cycle, another representation of the combustion process that takes place in reciprocating internal combustion engine. Auto power cycle was a typical spark ignition piston engine. Diesel power is a reciprocating internal combustion engine. One of the most frequent thermodynamic cycles that can be found in automotive engines. Diesel engines are considered the direct applications of diesel cycle. Diesel cycle consists of 4 processes, that is 1 to 2 is isentropic compression. From 1 to 2 when it goes, it is isentropic compression. Isentropic means entropy does not vary. In the TS diagram you see the entropy is constant here from 1 to 2. Then the process 2 to 3, that is constant pressure heating. Constant pressure, when we say word heating, that is temperature would rise. And when temperature is rising from 2 to 3, here you can see the difference of temperature between 2 and 3 stage in TS diagram, but this is constant pressure. At the stage 2 and stage 3, the pressure is constant. Then comes process 3 to 4, that is isentropic expansion. Now the expansion is here. Because expansion is there from 3 to 4, we have the volume increase. That is from 3 to 4, there is an increase in volume, and this is isentropic, the entropy does not change. Then comes process 4 to 1, that is constant volume cooling. Like heating was there, this was exactly opposite to it, constant volume cooling from 4 to 1, that is the entropy decreases, and when it is cooling, there is heat rejection. You can see Q4 to 1 is heat rejection, and there was heat addition Q2 to 3 when constant heating was there. Let me try to see some relations in diesel cycle. For instance, the efficiency of a diesel cycle is given by the relation 1 minus 1 by R bar gamma minus 1. You know R is compression ratio, gamma is our adiabatic index, and in the diesel cycle there is an additional factor, that is rho power gamma minus 1 by gamma into rho minus 1. So that is rho is cut off ratio, that is V3 by V2. This is ratio of cylinder volume after combustion to that of before combustion. And V1 by V2 is compression ratio, that is ratio of initial to the compressed volume. Adiabatic index is the ratio between Cp and Cv, that is ratio of the specific heats, where Cp is the specific heat at the constant pressure process, Cv is specific heat at the constant volume process. Usually this is around 1.4 for air. Let me directly come to a problem statement. In a diesel cycle, the compression ratio is 16 and cut-off ratio is 2. Just to recall, this is compression ratio R, this is cut-off ratio rho. Compression ratio is 16, cut-off ratio is 2. The compression ratio 16, I can put the value, R is equal to 16 and rho is equal to 2. The working fluid is air. When we say air is the working fluid, we put the value of gamma as 1.4. The initial pressure and temperature are 100 kilopascal and 300 Kelvin respectively. The initial temperature is 300 Kelvin and the initial pressure is 100 kilopascal. This is initial, I will put it as P1 and T1. Calculate the thermal efficiency of the diesel cycle. This is not a very lengthy or long numerical, only we need to calculate the efficiency. We need not to determine any of the P, V, T values at different points just to calculate the efficiency. Directly we will use this relation. We have R with us, gamma with us, rho with us, putting the values, I will find the efficiency. So, efficiency of diesel cycle is 1 minus 1 by R par gamma minus 1. This into the factor that is for the diesel cycle, that is rho par gamma minus 1 by gamma into rho minus 1. Putting the values, I have this as 1 minus 1 by R par gamma minus 1. The value of R is 16, that is my compression ratio par gamma minus 1, that is 1.4 minus 1. This into rho par gamma, rho is cutoff ratio, that is 2 par gamma is 2 par 1.4 minus 1 by gamma 1.4 into rho minus 1, rho is 2 minus 1. This gives me the efficiency as 0.61, or I can even say efficiency of diesel engine in this case is 61%. Actually, we had the variables with us and we calculated the efficiency. Sometimes the variables are not given, like the previous problem that we discussed in the previous part of the tutorial. You might have to determine the salient points, temperature, pressure, to find the values of the compression ratio, of the cutoff ratio, in which you see the compression ratio is V1 by V2, the cutoff ratio is V3 by V2. We could have found the value. Here you can see in this numerical, because directly these things were given, the cutoff ratio and the compression ratio and gamma. This renders immaterial the temperature and the pressure. These are not used in calculation of efficiency. Now, in diesel cycle, the heating and cooling are constant pressure and constant volume respectively. That is, constant pressure heating, constant volume cooling is there. That is there in diesel cycle. There is another cycle known as Brayton cycle, in which heating is constant pressure and cooling is also constant pressure. That is, it is not constant volume cooling. If it is a constant volume cooling, then it comes as the diesel cycle. So, this is Brayton power cycle. Brayton power cycle is a theoretical cycle for simple gas turbine. This cycle consists of 2 isentropic and 2 constant pressure processes. Brayton cycle consists of 4 processes, that is isentropic compression of fluid, that is from 1 to 2, isentropic compression of fluids, that is compression of fluid, the pressure increases, that is isentropic, that is entropy does not change here. And 2 to 3 is constant pressure heating process. 2 to 3 is pressure constant here, but it is heating process. 2 to 3, the temperature is rising. Then comes isentropic expansion, the process 3 to 4. 3 to 4 is isentropic, the entropy does not change, but it is expansion, that is the volume is increasing from state 3 to state 4. Then comes constant pressure cooling. Here this pressure is constant, you see here the pressure is constant from 4 to 1 and it is cooling here, that is temperature is also decreasing from 4 to 1. This is Brayton power cycle. I did not do any longer numerical statements in the diesel power cycle because I have discussed that in the previous part of this tutorial. Similar problems could be also discussed in the diesel power cycle or Brayton power cycle, but to just calculate the simple values here, I will try to use these relations. If nozzle expands gas to ambient pressure, that is isentropic expansion, then exit velocity is given as, that is VE, that is given as under root of 2 Cp into T4 minus T1. Cp, you know, is the specific heat at constant pressure process. The thrust of air is calculated by F, that is VE minus V naught. Here it is V naught entry, here it is VE, that is exit. The exit velocity is given by this relation. The propulsive efficiency, because we are talking about the gas turbine cycle, though it is a theoretical cycle, but for gas turbine it is entry, it is exit, it is propulsion efficiency or propulsive efficiency of nozzle, that is calculated by 2 V naught by VE plus V naught. So, let me just try to see two simple numerical statements here. First problem says, turbojet engine flying at an altitude where air enters the diffuser at 250 meters per second. The pressure ratio across the compressor is 10. The maximum cycle temperature is 1300 Kelvin. Assume the ideal Brayton cycle behavior. Ideal means we will assume the theoretical ideal Brayton cycle behavior with perfect gases, that is gamma is given as 1.4 and Cp is given here as 1.005 kilojoules per kg Kelvin. The inlet temperature is 300 Kelvin. The nozzle expands the gas to the ambient pressure. Determine the exhaust velocity, the thrust per kg of air and the propulsive efficiency. What we have been given here is temperature of the entry as 300 Kelvin, inlet temperature. So, if I try to draw this nozzle just like the previous diagram, this nozzle is something like this, where the inlet temperature, that is T1 is 300 Kelvin and the velocity where the air enters to a diffuser is 250 meters per second, that is V naught is 250 meters per second. This is inlet and this is outlet. At the outlet we need to find velocity, that is VE is to be determined. So, what we have with us is V naught as 250 meters per second, temperature inlet is 300 Kelvin, maximum temperature is T max, that is 1300 Kelvin. If I try to draw this, it would be in such a way. I will try to draw the temperature entropy curve here at 300 Kelvin and the maximum temperature, that is 1300 Kelvin. The process would be in such a way that at some point there is constant entropy here and at the maximum temperature as well there will be constant entropy, isentropic process would be here. So, this process could be drawn in this way. So, because 300 is the inlet temperature, 300 Kelvin. So, here this is stage 1. From here it is a isentropic process till point 2, then it goes to increase the entropy, that is process 2 to 3, that is constant pressure heating. It is a constant pressure, but here the temperature is 1300 Kelvin. From here we have 3 to 4, that is isentropic expansion. From then 4 could be connected to 1. This temperature is all in Kelvin. Now this maximum temperature is our temperature T3, and we have been given gamma as 1.4 and Cp, that is specific heat at constant pressure process, that is 1.005 kilojoules per kg Kelvin, and pressure ratio across the compressor is given as 10, that is Rp is equal to 10. Now I need to find the exhaust velocity first, that is Ve. To find exhaust velocity, I need to use this relation. Exhaust velocity is equal to under root of 2 Cp into T4 minus T1, that is I need to determine the temperature T4. At T4, what is the temperature I need to determine? So for that, I will use the relation T2 by T1 is equal to Rp to the power gamma minus 1 by gamma. Therefore, T2 is equal to T1 to this value, where T1 is equal to 300 Kelvin and Rp is 10 to the power gamma minus 1 by gamma, that is 1.4 minus 1 by 1.4. This gives me the value of T2 as 579.2 Kelvin. My challenge here is to find the value of T4. At T2 the temperature is 579. This is 579. So T4 would be higher than T2. Now we assume that the turbine work is equal to compressor work. Assuming turbine work is equal to compressor work, that is Cp into T3 minus T4 is equal to Cp into T2 minus T1. This gives me T4 is equal to T3 minus T2 minus T1. Putting the values, T3 is 1300 Kelvin, T2 is 579.2 just calculated, T1 is 300. I got the value of T4 as 1020.79 K. Now exhaust velocity. Exhaust velocity, that is Ve is equal to under root 2 Cp into T4 minus T1. So I will put the values here. This is equal to 2 into Cp, that is 1.005. It is 1.005 kilojoules. So we need to convert that into joules. So this is 1.005 into 10 raised to power 3, right? This is added. So 10.3 is added because we are converting kilojoules, converting Cp from kilojoules per kg Kelvin to joules per kg Kelvin. That is why this value 10.3 is multiplied here. This times T4 minus T1. T4 is just calculated 1020.79 minus T1 is 300. So, I got the value of the exit velocity as 1203.65 meters per second. That means this exit velocity is 1203.54 meters per second. Next part is thrust per kg of air. The thrust per kg of air, to find the thrust, we will see or put the relation thrust F is equal to VE minus VO. It is a simple difference between them, that is 1203.54 minus V naught. V naught is the entry velocity, that is 250 meters per second. So, this difference comes out to be 953.65 Newton per kg, because this is thrust, it is Newton per kg. Next, it is asked what is the propulsive efficiency. For the propulsive efficiency, we will use this relation. It is 2 V naught by VE plus V naught. Propulsive efficiency, I will put eta propulsive, this is equal to 2 V naught by VE plus V naught. This is equal to 2 into 250 by 1203.5 plus 250. This comes out to be 0.34. Therefore, efficiency is 34%. I have another problem statement on the Brayton power cycle that I will leave you to work. I will just read it and give you certain hints on how do we work on this. An ideal Brayton cycle operates between pressure of 1 bar and 6 bar. The air enters the compressor at 300 Kelvin and exits the combustor at 1200 Kelvin. Assume the isentropic process where alpha, that is for air, is 1.4 adiabatic index. Cp is 1.005 kilojoules per kg Kelvin and air behaves as an ideal gas. Thermal efficiency of the cycle is to be determined. Net work output per kg of the air is to be determined. Here you can use the same relations that I used in the previous problem. That is, we will use a relation that is T2 by T1 is equal to Rp per gamma minus 1 by gamma. This will give you the value, and you can again equate the compressor work to turbine work like I did in the previous numerical. Then heat supply, that is Q in is equal to Cp into T3 minus T2. Using all these relations, you can try to find the thermal efficiency and net work output per kg of the air. This is a problem for you to solve. You will get the solution in the notes file. I will solve it here and give it to you, that you can check your results with what I have calculated here. With this, I am closing my tutorial 3, which was on power cycles. It is delivered in 2 parts. I will come with another tutorial, tutorial 4, as the next lecture, which will be covering the psychometrics. Thank you.